Let's talk about BERT. BERT stands for bidirectional encoder representation of a transformer. It is state of the art language model developed by Google. Okay. So it caused really stir in the natural language processing industry because this is also called an ImageNet movement for NLP. Okay. A lot of times, in NLP, we need to keep training embeddings from the scratch for every new application. And a lot of times, if the data is not available, the training becomes hard. So BERT allows us to do transfer learning where you can use the embedding which are already trained by Google, and they have used Wikipedia and books online to create the BERT embeddings, and you can just use it as it is, these embeddings, and use transfer learning to just learn it for your domain very quickly with a less amount of data. And the BERT is found to be performing very good uh, in a specific domain just by retraining the last layer. Okay, that's why the BERT is becoming extremely popular these days. The original use of the BERT, the basic unit of the BERT, is nothing but it's called a transformer. Okay, you can feed in the word in French, for example. This is the input to the BERT. This is a French sentence, and the BERT transformer then generates an English. It can generate an English output. This is one of the use case, right? That's the basic unit in BERT. Okay, let's learn a little bit more about that. So the transformer gen we can explode further. Basically, it contains of two things: encoder, which encodes the input sequence of word into embeddings, and then the decoder, which again convert those embeddings back to the final destination sentence, which could be in English or it could be any other language. Okay, so a byproduct of this transformer then is the word embeddings, right? That you can use for any other task like sentiment analysis, news classification, movie reviews, just to train your model quickly using those embeddings. Now, if you go a little bit deeper into encoder and decoder, there is not only one encoder and decoder, there are multiple layers of encoders that are used. Encoder 1, encoder 2, this is the input, and these encoder output then just feed to each other. There could be up to 6 to 12 layers of encoder that are used, and they just feed into each other. And similarly, there could be multiple layers of decoder: decoder 1, decoder 2, decoder 3, and the final decoder. And the output encoder can feed into all of this, and then the output is generated, right? That's those. So there are multiple layers of encoder and decoder. There is not just one. If you want to look into encoder further, basically the encoder looks something like this. The encoder has two major blocks. One is called self-attention, which is basically responsible for learning the relationship between the nearby words, and the self-attention then feeds into a feed forward neural network. then generates the embeddings, right? This is the encoder. This is how it looks like. And the decoder is slightly opposite of the encoder. So a decoder looks something like this. So it is again having the self-attention layer, and then encoder decoder attention, another layer, and again a feed forward neural network to generate the final output, right? So these are the individual layers which are present in the input layer. Okay, now let's understand more about the self-attention layer. A self-attention layer is basically responsible for learning the relationship between the words, right? What it basically means is, for example, let's say you have a sentence called the animal did not cross the street because it was too tired, right? So remember, here is a word it here, and we want to make sure the word it is somehow related to the word animal here. So this is captured by self-attention layer. So let's say if you draw a co-occurrence matrix, the animal did not blah blah blah, and here again you draw the animal, same thing, and let's say word is here, is it? We find that the self-attention layer makes sure the relationship between the word it is very high with a probability of 1 as compared to the other probability, let's say 0.78. So self-attention mechanism ensures the words which are related close to each other, even if they are far away from each other, they are the relationship is captured. Okay, now let's learn into detail how the self-attention mechanism works. So in the self-attention mechanism, you saw the input you have basically let's say you have two words called thinking and playing. The first thing that BERT does, it converts this into embedding, which is of the 512 dimensions. Okay, so let's call it as x1 and let's call it as x2. Okay, this is the 512 dimension embedding that's the word does. Then internally for each word basically for each word BERT generates three vectors: query vector, key vector, and value vector. Query vector, key vector, and value vector. And this it does it by using equation x multiplied by wq, give me q vector, x multiplied by weights wk is equal to k, x multiplied by wv is equal to v vector, right? Where x refers to the input vector, wq, wk, wv are the weights which are randomly initialized by the model first to generate these vectors, and then later on based on the error these metrics are adjusted. So once we have this input vectors, so what we do is we first compute the score. We compute the score q1 into k1, and let's say it comes up to 112, and then we similarly computes q1, the same word vector with the multiplied with the uh, query vector of another uh, key vector of another word q1 into k2, and then you compute 96. So this will compute the relationship between the words. Then what we do is we divide by 8 these vectors. So this value will be 112 divided by 8 is 14. 96 divided by 8 will be 12. Okay, then we do a softmax function which will map this and this probability together on a scale of 0 to 1, and this probability will come out to 0.88, 0.12, and softmax will ensure that sum of this and this probability is always 1. Then what we do is we multiply each of this vector into by the value vector that we got, and then we sum it. So v1, v2, and then v1 and v2 we compute, and then we sum all the v1 v2 to get z1. The same process you do to get z2 for the second word. So we repeat the process for each word. So just to summarize, first we compute for each word, we first compute the 512 dimensional vector. Then for each word we randomly initialize q1 query vector, key vector, and the value vector. And then we first multiplied by, for each word we multiply by each query vector into its key vector. Then each query vector we multiply with the key vector of every other word. Then we divide by 8, we softmax. Then we multiply it with the value vector. Then we compute the sum of them all the vector to get a z1. Similarly, we distribute the process for word 2 and we compute the vector z2, right? So the value vector is basically ensures it has a weightage, low weightage for frequent word like is, this, the, and more weightage for the important words. So it basically reduces the weight for unimportant words and amplifies the word for the rare, amplifies the effect of the rare words, right? Now let's understand another thing in BERT known as a multi-headed attention. So you saw the earlier how we generate z1, z2, z3 vectors, right? So each word has associated q1, k1, v1 vector, and then from that we generate these vectors, right? Now very often it's quite possible that one word is associated with the multiple words, so that's why we need a multiple sets of query, key, and the value vectors. So that's why it's called a multi-headed attention. So the way it helps is, let's say again, if you take an earlier example, the animal didn't cross the street, blah blah blah, and similarly there was it word here, other words. So it could be related to the multiple words animal with the 0.98, and it could be related to the other words like say tired, because it still refer to the it as the animal as the same subject, 0.88. So this multi-headed attention allows us to have attention of the word vector to the it, to the animal, as well as to the word tired. That's why multi-headed attention is very very popular. So these words, right, are further then fed to the decoder layer, these vectors, or feed forward layer to process it further and to reduce the loss. So that ensures the process is repeated, the feed forward layer. The feed forward layer is fed to the decoder layer, right? The decoder layer then generates the required output in a specific language. Okay, so the way It is the BERT is trained is, let's say if you have the sentence like I like NLP deep learning, so it basically masks 15% of the word. Okay, so let's say it masks NLP and it creates a training example I like mask deep learning. This is the input and the output would be NLP. Okay, so it generates all training examples internally and then it trains its model in such a way that this it learns to predict that this mask is the word NLP, and in the process it learns those weights in the model, and then these weights are used as embeddings, right? So what tends to happen is, so for word I, it could be represented as vector like 0.9, 0.6. Similarly I, so for each word it can generate the vectors 0.96, 0.98, blah blah blah. The dimension could be 512 or 1024, right? So it basically emits those embeddings, and that you can use in the process like sentiment analysis, then language translation and things like that. So an interesting effect of any word embedding, just like Globe, is if you plot those embeddings, let's say it's a vector of a man, vector of a king, vector of sir, then vector of woman, vector of queen, vector of madam. Interestingly, you will find that the distance between man and woman vector is almost same as the distance between king to queen or distance between sir to madam, right? So semantically, the words, the semantic meaning of the words can also be represented of algebraically, right? So what I'm saying is the difference between queen vector and king vector will be same as the difference between a woman vector and a man vector, right? So this kind of interesting properties can be expressed algebraically using the embeddings, and of course we can use these embeddings to train movie review, sentiment analysis, and a lot of other applications. So these are generic embeddings that can be used in a lot of NLP applications, just like fast text or even word to vec or globe embeddings. This is absolutely state of the art. If you compare the performance of globe embeddings, you can just look up. It's pretty awesome performance of BERT embeddings as compared to globe. So if you look at the performance of the BERT, here are the different models. Like BERT has different model based on the complexity and the accuracy, how much you want, light version, heavy version, depending on the number of dimensions. So you can see it has the comparison of the BERT with the ELMO or with the BiLSTM models. The BERT happens to be the accuracy, even the F1 score of the BERT is a lot better as compared to models like BiLSTM or even OpenAI GPT or other models. So BERT is very popular and it's really catching the world fast.